It's about heavy-duty vehicle multiplexing, part 1. I'll get back to that. And I just want to spend a couple minutes thanking everybody that actually keeps on coming on to these Dorman Products Lunch and Learns. And by the way, again, Dorman, I can't thank you enough, but I'm so totally impressed with the regulars that keep coming on. I name them all, you know, guys like you and me, Gino from my area. Gino, thanks again for sending me the Pico waveforms. I'll probably wind up using him a little later, but I've known Gino for years, and got Ryan from the other end of the Canada way up there, you know, in the cold part, I guess. You know, Mike, you know, he's always texting me, you know, and just so many good people. Jim Wilson, you know, I noticed quite a few trainers, they come on. And Jim, by the way, I hope everything is going well with you, my friend. I've actually noticed there's a few people that are into the more of the, I guess you might call it, the enforcement of emissions from other states, Stephen, Layden. But there's so many, and I can't just, again, I'm totally impressed. And once in a while I'll see there's guys coming in from different foreign countries, and, you know, hopefully you guys, and I know a lot of people in foreign countries speak English and understand English better than I would with all the different languages that we have out there. So good for you guys, you know. But the reason I actually wanted to mention that is that, you know, no matter who we are, we're all in the same boat. This week happens to be Technician Appreciation Week. And I just want to spend a couple minutes to tell you guys that I, for one, I truly appreciate what you guys do. And actually it was started by ATA, the TMC. They've had a driver appreciation week for, I don't know, 30, 40 years, if not longer than that. And sad part of it is, when I Googled these couple of things, I mean, the driver appreciation is all over the place. I mean, I'm telling you, all over the place. I mean, companies with banners in front of their buildings and stuff. And compared to the drivers, if I get just a little fraction of somebody mentioned technicians, it's a lot. So I'm going to give you my take on that, guys, to show you how I appreciate it. And I include myself into it too, that one of the biggest driving forces to keep the drivers happy and keep the vehicles kind of safe is the pre-trip, post-trip program. And of course we have in our country, and Canada too, we have the roadside inspection program. So the easiest way to reward the drivers is technically if you come in with a good clean inspection, which absolutely is a positive for, you know, the CSA scores, which leads into insurance rates and so on and so on. They usually get rewarded with something, but I have a look, and again, they deserve it. Don't get me wrong. That's not what I'm trying to do here. But I think the world also needs to realize that these drivers would not get clean inspections on the roadside if it wasn't for guys like me and guys like you, okay, that actually get dirty, crawl underneath it. Doesn't matter if it's wet, snow, rain. I mean, who gives a shit? I mean, we're under there and we're doing it. And this, another point I'm going to also try to make is that today's Lunch and Learn might be a little spotty because I've been balls to the wall all week. I mean, you know, we've had nothing but, I mean, it's been a hard 8 week working on everybody, trying to please everybody with their trucks and stuff. So believe me, I definitely know the heartaches and all that stuff. You know, I've screwed up my elbow here and everything, just no different than you guys, okay? So again, from me, thank you so much. You know, you guys definitely pat yourselves on the back. So let's get into this program here a little bit. Let's see what kind of trouble we're going to get into. Again, heavy duty vehicle multiplexing part 1. Okay. Dorman, again, they've taken the ball, Dorman and Chi, you know, and they've rolled with it, and they're actually trying to do something for the heavy-duty market. And I get it. You know, the lunch and learns I do on the heavy-duty end, they're kind of like, they get a little bit more in-depth, so they don't get the hits like, you know, the automotive or the little shorties that you see out there, you know, thousands and thousands like that. But I'm okay with that, you know. What's important is you guys walk away with something. And I'm, again, as usual, if you guys seen my lunch and learns, you know, I don't care about that portion of it at all. You know, what are we going to cover today? We're going to try to cover introduction to multiplexing, controller basics, PCM, ECM, controller area CAN. I'm going to utilize J1939 because, you know, you're not really... Yeah, we have a lot of older vehicles. We went through the transition with the J1708 and so on. But I'm going to jump right into utilizing J1939. You know, it's a good way to actually get into CAN in some of those areas. Now, look at this part one as just the beginning of another journey. I'm going to keep this continue, you know, whatever it takes. I just, you know, if it comes in my head, I'm going to do it. Part two, of course, will continue the journey. Now, I'm going to tell you, the problem with doing these lunch and learns is they're only an hour. I can only squeeze in so much. Okay, and this is going to be a perfect example. I'm going to try to keep it generic, okay, because let's face it, in today's world, in the commercial motor vehicle world, just take a look what you got. I mean, I don't have to tell you guys, you name the trucks that you have out there, the Max, the Volvos, the Internationals, the Freightliners, the Kenworths. I mean, they're all out there, and any given day, any one of those vehicles can have a Cummins, a Detroit. Packard's got their own engines, and International, and so on. Couple it with, think of the transmissions, the Eatons, the Meritors, I mean, automatics, manuals, ABS. I mean, you have such a conglomerate of manufacturers and components squeezed into this, you know. But the issue is that they all have to communicate. So for the communication purposes, I'm going to try to keep it generic. And the nice part about with you guys being on, it's a variety, guys. There might be guys, and I do the same thing in my classes, my actual live classes. You might have somebody that this is their first exposure to something. And I might have guys in there that have been doing it forever and ever, longer than me. I doubt if anybody's doing it longer than me, but just kidding, yeah. But my point being is, I can't kind of like try to please that person, try to please that expert person. But you know what, guys? And I can miss something too in this, or I might have forgotten, or else the biggest problem is I will go in such a hurry fashion. I'm looking at the clock that's way up there that I see, you can't see. So I'm like, time. So if I say something and you guys have experienced something, guys, that's what the chat box is there for, and I truly appreciate you guys networking and everything. So let's jump into this. Let's see what we can get into. All right, multiplexing. I took this from Wikipedia, free encyclopedia. In telecommunications, excuse me, in computer networks, multiplexing, also known as muxing if you're a computer geek, is a process where multiple analog message signals or digital data streams are combined into one signal over shared medium. The aim is to share expansive resource. So for example, in telecommunications, several phone calls may be transferred using one wire. It originated telegraphy, is now widely applied in communications. And we're going to build off this concept. And those pictures that you see over there, okay, this is a perfect example. I don't know how old you guys are, but boy, that's a lot of wires coming off of that pole. You know what they are? Each house had a telephone wire going in there. It's like, you kidding me? No, I'm not. That's the way the world was. So we came a long way with this, you know. So now let's jump into the trucks. The heavy duty truck multiplexing network, okay? In a typical truck, there's also a lot of signals and data trying to talk. At the same time, a lot of controllers trying to listen. No different that I'm over here, standing here. I grant you all I got is a chat box to look at, but we could be in a crowd and we could be talking to each other, okay? But you know what? I might get into a crowd that it's like, really? I really don't care what you're saying. So that's going to go in one ear and out the other, okay? However, in that crowd, another person talking might have a subject that I might really truly care about, and so on and so on. I will definitely tune them in and ignore you. Not you per se, but you know what I'm saying. Okay? Unfortunately, I might be stuck listening to all the conversations regardless. This is where selective hearing comes in. I do that with my wife. I'm just kidding, guys. Just kidding. Don't ever, if you have my phone number, don't ever let my wife know this, But let's substitute us to the controllers, computers, whatever you're happy utilized in these trucks. Overview. Today's trucks have numerous electronic control units, ECUs. Again, I don't care what you want to call them, okay, to control the subsystems. They're really controllers. And I just give you a little minor list here. Engine, transmission, brakes, lights. Don't forget infotainment, instrument clusters and so on. And again, these controllers are networked together to share information. And that little dashed line that you see over there, okay, don't go by that. We're going to get into double wires and parallel and stuff like that, even single wires and stuff. This is just a representation, like I said, I've had a very rough week, of its simplest form of what it might look like. And there's your vehicle speed sensor, and if you look at that, chances are pretty good, I'll back that up, chances are pretty good, all those things will have to get some kind of vehicle speed information, depending on the vehicle, But anyway, why multiplexing? In the day when life was simple, trucks were also simple. Most functions were directly managed by the driver using mechanical, hydraulic, pneumatic. So I put in an example here, the accelerator pedal connected to engine control unit by mechanical linkage. Really? Yeah, just kidding. But yeah, those were the good old days, okay? Electrical functions were typically hardwired to switches on the dash through relays to actuators. Look, just like cars, trucks throughout the years became more complex, requiring more miles of wire to enable the electrical mechanical system to manage the vehicles. And of course, this ultimately required the use of data bus communication. And this is nothing, I want to throw in here too. This data bus stuff and networking, that's been around for a long, long time. It's just we are getting more and more into it, as each year goes by. I mean, they're really relying on that, and we're starting to see issues too. Benefits depending on how you look at it. And I guess the reason I put that in there is like, wow, here we go again. I remember the days when you were able to go up to a light bulb and just, if the bulb was out on that truck, you basically, it was either a bulb or it was power or ground to it, nothing complicated. And slowly but surely everything changed, went through the body controllers, and now the driver comes in and he's got a light out and you go do your most simplest task, you jump right into it. It's not really rocket science, but it's rocket science once you wind up being, it's like, oh, it ain't the bulb, it ain't the wires going to it. Now, where are we heading with this thing? Are we going into chassis, body controller? Where are we having the problems? And here we have a truck sitting here for a simple freaking bulb, and all of a sudden, maybe who stocks these controllers and stuff unless you're a dealer? And I'm just using this as an example. It might be a little extreme, but all of a sudden, this guy is down for the count because he doesn't want to go on the road. He's got no stoplights or whatever the case may be. Safety comes into the play, and here we are. Because of electronics, this vehicle is down. So again, that's my 2 cents. Okay? But again, what happened was many cases replacing relays, circuit breakers with electronic devices. Okay? And I've brought that up before in a few different lunch and learns. The electronic devices, like I said, I like calling them controllers. They communicate over the vehicle data bus, monitoring inputs, sensor switches, and of course, don't forget supplying power to the outputs. So let's simplify it. A multiplex system continuously monitors inputs and sends messages over a shared wired data bus to control outputs. Data bus communication makes use of multiplexing since the first use of electronic control modules. Again, like I said, it's nothing really new. Go back to the 80s. The first use of multiplexing were a simple module to module system. Can't get any easier than that. And in the day, it really didn't require an understanding of the systems to diagnose the issues. Okay? Typical systems might be an engine manufacturer allowing a chassis module to communicate with a fuel injection control module. You know, today's technicians, we're going to have to access the truck's data bus connecting several various modules, controllers to read, diagnose, repair any issues. Simply put, the multiplex system can interpret different messages transmitted on the same wire. Messages traveling along, and we call that a data bus. The data bus handles multiple messages at the same time. Electronically controlled transmission connected to the engine to control engine speed and torque output during shifting is a good example of that. Okay. So when I put this together, I started saying, wait a minute, I'm jumping right into multiplexing CAN. I'm kind of putting the cart before the horse, and I don't want to do a computer course at this point right now. But I figured, let's jump into the computer at this point, so we kind of get an idea where it fits into the scheme of things. So a computer system basics. After all, it's the controllers called computers, nodes, as you get in deeper, they must talk with each other. So what is a computer? It's an electronic switch. Keep it simple. That's all it is. It's a switch. It processes information very fast. It contains instructions. Okay. You're not the one interfacing to throw those toggle switches. This guy's got to decide, should I, turn that switch on or off, or should I do this, and so on. So that's where the instructions come in. They're embedded in the memory. Most computers can process millions of instructions every minute. I think us guys are pretty good in our brain. We could probably do the same thing. We don't even realize it. If you're talking to me, if I'm looking at something, the visual aspect, if I smell, I hear and stuff, I think my brain's capable of doing. So that's why sometimes we have a little problem with these automated vehicles, these autonomous vehicles. Can they really think as fast as we can? I'm going off the tangent here, guys, but I don't ever want to put myself or you guys down that computer is better than us. The speed of processing information makes a computer ideal for controlling a vehicle operation. Basic function of the computer is, again, receive data, process the data, and or store data, it outputs signals. Keep it simple. Computer controlling a basic system. Sensors send a value to the computer controller, call it an input. The input value is used by the computer to determine the conditions of the monitored system. The input value is compared to a pre-programmed value in the computer's memory and decides on an action to take. The decision is converted into an output signal. And that output signal, let's face it, controls something, control an output device. Or, don't forget, reports information to a diagnostic system or something as simple as a warning light or dash gauge. Don't forget, you're hooking up to a scan tool. It's going to tell you what's going on with that vehicle, what's going on with that engine, what's going on with that transmission, and ABS and so on. Now, this is just basically showing you get my face out of there. Graphically, you got the analog sensors, AD converter, inputs and outputs, okay? The input signals are generated by either analog or digital sensors. So, I'll give you an example. How about a crank and cam sensors? A lot of people will call them a revolution sensor. How about temperature sensors for air, coolant, oils, and so on? And I already mentioned switches. Don't forget the on and off switches. Output signals drive actuators such as injection units, ABS solenoids, fuel pressure control solenoid valves, and so on. And you can make up your own list. So graphically, you know, that's what we have here. By the way, if you look in the middle over here, just in case I forgot to mention it, okay, we're looking, you started out with that in the middle one here, right here, okay? Analog, digital. That AD converter is there for one thing. This guy here don't understand this, the analog. So there's an analog to digital converter inside there. First of all, there's something in there that's going to amplify this weak little signal here, and this converter is going to change it to digital, on, off. That's its language, bits to bytes and so on. So I had to throw that in there, guys, you know. And again, you know, there's all sorts of stuff in there. Right now, we're going to try to keep it as stupidly simple as possible, okay? In the real world. So let's take the simplicity and let's apply it someplace. And I decided to apply it on a fuel injection system, okay? Utilizing, of course, today, most of our systems are the common rail fuel injection systems. This fuel injection system utilizes a crankshaft-driven fuel pump to provide pressurized fuel to a rail. Distribution lines transmit fuel from the rail to individual injectors serving each cylinder. And again, this is generic, guys. This is generic, okay? The ECM turns on fuel flow from each nozzle as part of the injection process. No, the pressure in the rail is very high. And guys, it is very, very, very high, and it keeps getting higher, and a lot has to do with reducing emissions and so on. You know, comes around in a circle, okay? But regardless, supplies this high pressure fuel to all cylinders that is going to vary with the operating conditions, and the pump providing this high pressure fuel is not electronically controlled. Again, I'm keeping it generic right now. However, the ECM does monitor data from the rail pressure sensor to determine when rail pressure drops below or above a target. So ECM is monitoring something, isn't it? It's monitoring the pressure. If the pressure exceeds the limit, the ECM adjusts a metering valve to increase the flow of fuel from the rail into a drain line until the pressure data indicates rail pressure has fallen into an acceptable measurable range. If the pressure in the rail is too low, the ECM adjusts the metering valve to allow less fuel to flow from the rail into drain return line. Sounds something like a closed loop, doesn't it? If you guys work with cars and everything, you know, what are we controlling in there? Same thing. This described a closed loop system because the ECM controller adjusted the control device, the metering valve, based on the input sensors. That's monitoring the effect of the adjustment. It's closed loop. Okay? Stop. With this basic information, would you be able to start a diagnostic process for a no-start rough running? What data would you monitor and scan to? Just think about it. What's the ECM monitoring? Shouldn't you be monitoring that yourself? Other examples, again, ABS, fuel emission control, using O2 sensors. How about gas recirculation systems and after treatment systems? I mean, you guys can go back and I'm sure you can come up with so many systems that will work similarly. Okay? Data received, inputs, information. Again, I mentioned two types of data. Digital signals, they're going to vary between one or two states. And I already mentioned either on or off, 0 or a 1. Computers perform their operation on digital data, and I mentioned that to you already. Analog signals vary with an acceptable range, usually a voltage level between 0 and 5. And there's some, technically, I shouldn't even be getting into it, but there's an area between 0 and 0.4, 0.5. If it sees it in there, we have an issue. If it sees it from 4.5, 0.5. But anyway, let's keep it simple, 0 and 5, okay? So if we use a temperature sensor as an example, 5-volt signal, again, it's just an example, would indicate highest temperature. So if we go down the other end, 0 volts would indicate lowest expected temperature. Each voltage level in between would correspond to different temperatures. Do we have enough information to figure out any issues? Absolutely. You know, if you're working with temperature, you can watch voltages and so on. That's the whole idea of what we're trying to do here. How computers think, right? And like I said, I don't want to overcomplicate stuff. Computers speak in ones and zeros. To be honest with you, I don't know that language, and neither do you. You know, I shouldn't say neither do you. Maybe some of you, there's guys out there that are watching right now. I mean, you get super, super deep into it. But for me, I'm looking to fix a truck, you know. So I don't necessarily, you know, I'm not designing computers and so on. So I'll leave that to the smarter people. If we want to talk directly to one computer, listen on conversations between several interconnected computers in the same vehicle, we're going to need an interpreter to convert all those ones and zeros into words and messages that we can understand. And one of the ways, of course, you can see it visually. You see the Picolab scope waveform over there. So visually, you can see things that happen, okay? Scan tool definitely is an interpreter. Our dialogue with the vehicle computer begins when we use the scan tool to enter a request for data. We may ask for information about fault codes or about the current state of engine sensors. Computer responds to a request. Again, scan tool is our interpreter. Scan tool converts data from the vehicle computer into words and measurements and displays them on the scan tool display screen. This guy is the middleman, the interpreter. And we do rely on it, you know, in our communication with that computer, that interpreter, okay, that middleman for our communication. Okay? So that's so important. I'm messing with you guys. Looking at the chat box, people, I can't hear you, I can't hear you, I can't hear you, okay? So the problem is there a problem? We just lost communication, didn't we? Okay? So the thing is the problem with your computer speakers? Hey, with everybody sending those alarming things, one of the problems is on my end. How would I know if it's on mine? First, I was able to see in the chat box, you guys alerted me there is a problem. So right away, you know, think about it like the scan tool, think about on your dashboard, you know, lights come on and everything. You guys told me there is an issue, okay? However, with all of you having the same issue, the problem must be on my end because all of a sudden everybody's telling me. So it's like, oh, shit, it's got to be me. How can I quickly determine it's me? I have a mini box that has a display that every time I talk, a signal generates a digital display that I can visually observe. On that box, no graph movement will indicate my microphone signal is not reaching that controller to pass it on to all your computers. So if you assumed the problem was on your end, you would make sure your speaker is on. You might even reboot your computer. I mean, in vehicles, don't we once in a while do that too? Or switch to another app with sound to see if it works. If it works, you know the problem is on my end. Process of elimination. I did this on purpose just to try to point out the fact that, you know what, we are capable of figuring stuff like that out. And to be honest with you, that actually happened in one of my lunch and learns. And I don't want to pull it out, it's too hard to put in. But if you, yeah, I'm not trying to show you my butt here, guys. But there's a wire that goes from my speaker up here, I got it running through here, goes in here, and it threads into this connection over here. No comments, guys. And I lost a whole sequence, a whole lunch and learn. Didn't realize it until we went to play the recording. And guess what it was? Yep. Connection on my butt, not my butt, that transceiver. I couldn't believe it. I said, holy shit. And it's like everything else when we work on the vehicles, you know what it was? It was a loose connection. Go figure. But it was devastating for me, so I had to do the lunch and learn all over again. So let's see what else. Was this simple enough so far? The microphone I am using is another example of using electronics to generate a signal. And there's others, okay, but I'm using this for an example for a reason. Crystal microphones use a phenomenon called piezoelectricity. That's a huge word, you know. I'm just a little old, not into so many big words, you know, but we'll walk with it. We'll go with it. What is it? Stability of some materials produce a voltage when subjected to pressure to convert vibrations into electrical signal. Okay, that's nice, but where else do you see this piezoelectric concept used? I don't know. Let's find out. How about the automotive market? Today's vehicles are incorporating more sophisticated sensing technology, utilizing piezoelectric ceramic products. And again, this actually, just so you know, years ago when I was doing automotive trainings and stuff, when we got into OBD and everything else, and we had to, you know, get in map sensors and all that stuff and everything, believe it or not, what's in that map sensor? You got it. You got a component in there, you know, that piezoelectric ceramic product is in there. Okay? And basically when you squeeze it, you're going to get in a signal, electrical signal out. It's that simple. So it's not necessarily new, okay? So some common uses: injectors, actuators, sensors, sense, control, just a variety of different systems. An actuator converts an electrical signal into very precise physical movement, stroke. I'm going someplace with this. Good example are piezo fuel injectors. We use them. Why? Because they're more accurate, open and close the pintle more rapidly, and they're more precisely, then you can get or develop or wind up with a more precisely controlled fuel spray. And that's huge in reducing emissions and so on. So everything is, I got to tell you in all honesty, if you look at your car, you look at your trucks today, especially on the engine side, you know, everything you have today with electronics and control is really, it's emissions driven. You know, just think about it. Go back and, you know, do some search and you'll see, you know, when I started, I went through the whole transition from the mechanical stuff to this and stuff and so on. But anyway, the piezoelectric pressure sensors, these sensors respond to pressure, acceleration, or other inputs by producing an electrical signal. Signal is relayed to the vehicle's computer or computers. So throughout some examples here, tire pressure sensors, dynamic pressure sensors. Many sensors are being used and developed for so many safety features of today's vehicles. These safety devices include faster control braking, airbags, crash avoidance and stuff. And they're in the cusp right now, trying to figure some of those features out. They're not totally perfect. What I'm reading or when I talk to drivers and stuff, they're not perfect, you know, so, you know, a little bit of a warning, just because you got those safety components in there, you still need to drive accordingly, you know. So let's simplify this piezoelectric. Piezoelectricity is a charge created across a certain material when a mechanical stress is applied. Thus, piezoelectric pressure sensors use this effect by measuring the voltage across a piezoelectric element generated by the applied pressure. Voltage proportional to the pressure. Typical materials for sensors are quartz and tourmaline. But however, we also have what we call an inverse piezoelectric effect, applying voltage to the material, causing it to change shape. And that's where our fuel injector comes in. Hundreds of little piezo material slices stacked on top of each other to increase the motion of the pintle due to the combined expansions. Okay. And here's just a picture of one, you know, you have it in your handout, and, you know, digest it all you want. You'll see the actuator module and so on, nozzle module. You know, the internal, they can get quite complicated. How it works, okay. I mean, when you look at that in thousands of an inch of movement, move the pintle far enough to inject the fuel. I mean, that's not much, guys, at all. The expansion of the piezo stack causes a pintle to be lifted. And again, I'm not going to get into it, you know, when they put electricity, they want to expand, but however, you're trying to lift the pintle, so you have to go through a bunch of levers to achieve the right direction. However, once you go through that process, the fuel spray begins. When the injection is complete, voltage cuts off and the piezo stack shrinks and the spring closes the pintle. Now, this is a communication seminar. Piezo injectors provide feedback by producing fluctuations in the electricity used to activate them. It's a hell of a feedback going back to the computer, so the computer knows exactly what's going on. So if the engine control module calls for a certain injector opening time, say 0.5 seconds, and the injector response shows it open for only 0.49 seconds, the computer can add a very small bit of time to the next injection cycle to compensate. Also, by applying a little less electricity, the piezo crystals expand less, allowing the injector to open only part way, and that makes for a longer injection time. Speed, and that's the thing with communication that we're trying to get across. Speed, 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 speed. The speed of piezo injectors can also allow multiple injections during a single combustion cycle. To accomplish this, take speed of communication to sense, decide, and control. That means very fast data exchange speed. You know, as a side note, just so you know, if you lit up your grill or whatever, and those of you that use a cigarette lighter, but you're using piezo electricity, okay? Pressing that button causes a spring-loaded hammer hit a piezo crystal, producing voltage, electrical current that flows across a small spark gap, igniting the gas. Now that we have a little more knowledge, shouldn't be too complicated if you build a foundation, knowledge base to put it all together. Okay? So what do we learn so far? Not much, just kidding. I hope we learned something. Trucks have many controllers. Controllers are decision makers, but more importantly, they control. Computers need input so they can properly output. And you've heard that phrase 100 times, thousands of times in your life, garbage in, garbage out. So the input is so important. Today's sensors, actuators need to be very precise, very fast. The world's changing. The trucks are changing. Today's trucks network the various controllers and devices in the chassis to simplify the hardware. Eliminate miles of wires, thus reducing the number of pins on modules by sharing. Okay? Little note here again, instrument panels are a perfect example of reducing wires, okay? And you can see my previous lighting lunch and learns. By using smart switches and so on and sharing various electronic signals, there's only a minimal need for hard wires. In case you missed it, this is what I did in my lighting lunch and learn. You know, it was a whole hour presentation again, you know, do as much as I could in lighting. But again, I mentioned that lighting isn't a simple case. You throw a switch on and then you're just sending a little, you know, power over the light bulb and, you know, it completes a ground circuit and voila, the light comes on. Those days are gone. This is typical, okay? You see the chain 1939 twisted wires in there and the off, park, headlight, those are all smart switches, okay? So they're communicating back and forth, eh? And of course, this is from a freight liner, so you see the power distribution models of PDM, no relays. Where's the relays? Relays and a lot of that stuff are inside the computers today, okay? So again, you can revisit that, you know, to get a better idea, but I did put it in here just in case you didn't or you missed it. So we'll walk through this for a second. When the headlamp switch is turned on, The bulkhead module, it's going to sense that input. The bulkhead module is programmed to know which outputs to activate and where the outputs are located. You know, for example, are they in a bulkhead module, chassis module, or any other controller? Okay. In this case, the output for the left headlamp, low beam are located on the bulkhead module. And the outputs for the right headlamp are located on the chassis module. The bulkhead module directly activates the left headlamp, not the left and right, the left headlamp low beam. Because the right headlamp low beam outputs are on what? Absolutely the chassis. So they split it, okay? The bulkhead module does send a message over the J1939 to that chassis module, tell it to activate those outputs. And if you slow it down, just do it again in your handout, follow that sequence there. Once the chassis module receives the message, it's going to activate the correct outputs and sends message back, of course, to the bulkhead module, reporting the new status of the outputs. This allows at least one headlight to work even if one of the modules fails. Okay? Multiplexing uses protocols, rules, whatever way you want to look at it, okay? Regulations, rules, requirements, protocols, whatever you're comfortable with, to modulate electrons, messages from subsystems to subsystems. Reminder, the analog, again, the analog inputs, they are converted to digital. We did that few slides before by the receiving processor controller, okay? So that tells me, you know, we're not only talking just about the PCM PCM engine controller, we got body modules, chassis modules, transmission modules, okay? And that's why I like using the word controller. You know, they all in one way, shape, or another control something. These converted signals can then be broadcast digitally to other controllers on the network. They can also change back to analog format to affect actions. Look, this is why we need to be knowledgeable. So we are very comfortable looking at data and taking all sorts of electrical readings with our tools and testers. And guys, I'm going to stand right here and I'm going to tell you right now, I do not know every freaking vehicle, every scan tool that's out there, you know. Absolutely, I don't. I am constantly learning. Every time I get into another one, I get another one. One company's trying to do a little differently. And if you've ever looked at the wiring diagrams on some of these vehicles, the interaction with all the components that you have on a commercial motor vehicle is unbelievable. The different manufacturers, the cutoff points, you know, which part of it belongs to the vehicle OEM, which part of it belongs to the engine manufacturer, where do you connect, where do you meld them together, you know? So it can get quite complicated. So this is why I'm trying to keep it simple, so when you get to the complicated portions, if you have a minimal amount of information, it might at a minimum help you navigate through some of the more complicated issues. So typical data bus consists of a twisted pair of wires carry the messages. Example, using chassis information to share with other computer controlled systems. Throttle position sensor is the most often used as an example. Why? The TPS input is required for the engine management. However, transmission, ABS, traction control, collision mitigation, and so on, they're also going to need this input. How does it work? The TP signal communicates directly to one module, usually the engine controller. From there, it's going to broadcast over the data bus, paired twisted wires. so that any other controller on the network can pick the signal up. And again, you're looking at this graphics, this picture over here. This is simple, you know, we're not into snubs and so on, but try to keep it simple. You know, I'm going into the module, from that module is going to communicate to all the other ones, you know, depending on who it is. You know, one module could be, you know, ABS, one could be transmission, you know, and all the different modules that need that information will get it, you know. The following are common multiplex controllers, and that's another thing. I mean, yeah, they're kind of like, you see the commonality sometimes, but sometimes it isn't, you know, depending on the manufacturer. But for example, let's try to keep it simple. Engine control, ECM. Fuel injection control module, FICM. Transmission control module, TCM. Body control, PCM. Dash display, DDM. Instrument cluster, ICM. Anti-lock, ABS. Signal detection actuation module, SAM. Collision warning, collision mitigation, you know, and it goes on and on, okay? But if you slow it down and look at this, I'd venture to say that acceleration information is probably important to all these modules, or the majority of these modules, okay? And of course, that information does have to get there fast. All this is, guys, is just showing you a pictorial. This is a Volvo component locator. Man, I got to tell you, you know, no wonder we get all, you know, wrapped up and wound up, and, you know, and of course, if you're in a very small shop, or if you're trying to take care of a fleet, everybody's on your butt. I got to have that truck. I got to have that truck. Meanwhile, you're in the middle of trying to figure these things out, and before you know it, again, I opened up this by saying, guys, they need to appreciate us a little bit more, you know, than they're kind of showing. And again, don't get me wrong, I'm biased for what we do for a living, but I also know that there's not too many people out there are willing to do what we're doing. Because if they did, we wouldn't have a shortage of technicians, mechanics. All right? And this basically is, again, this is from my J Pro. And, you know, you might not see it too easy here, but over here, this is not a bus topology, but it also shows you, you know, where my power is going over here, you know, where it's switched. There's, you know, my battery, you know, and they're going everywhere. You know, there's my SAM. There's my engine, you know, and it just goes on and on. But at least I can see from the battery, you know, where am I going with this? What needs what? And so on and so on. So graphically, sometimes, you know, some of these scan tools do a pretty good job, okay? Most recent systems use a serial data bus system, keep wiring harness complexity to a minimum. That was the whole idea. Serial data transmission uses a single communication channel to deliver instructions, rather electrical signals to the controllers, modules. Most vehicles adopted the controller area network, CAN, not new at all, as a preferred data bus system. And again, consider it as a serial data transmission network used for ECM networking, comfort and convenience of electronics, mobile onboard external communications. Keep it simple. Major advantage is that should one of the modules fail, the remaining modules will still be able to communicate network. And again, don't cast this into stone, guys. You know, not always so either. Just wanted to throw that in there, you know. Of course, CAN 2, you know, we've progressed into, you know, faster, and, you know, we use CAN 2. And that CAN 2 is the basis for that SAE J1939. And that is the high-speed network standard used by trucks and buses and other vocations too, guys, just so you know, okay? The J1939 bus is designed to function from 125 gigabits per second up to 1 megabits. That, guys, that's fast. However, the nice thing about that With the J1939, it does allow for speeds as low as 10 gigabits. 500 seems to be the maximum, making a Class C bus. Okay. Now, little note, this is, like I said, it's been around for a while, equivalent to the automobile can. I don't want to get overcomplicated and get into the differences and blah, blah, but they are so damn close and similar. Multiplexing clock speeds, okay? Microprocessor clock speed translates to an ability to make the binary decisions per second. And that always gets me. Millions of binary decisions required to process a simple output command. So where does the clock speed comes in play? Clock speeds of at least 16 megahertz are required for J1939. Most current truck engine transmission processors have clock speeds of up to 32 megahertz, excuse me. And where might you have seen or heard about this 16 or 32? Me personally, every time I have to get a new computer, I look for that kind of information, my personal computer. So you might have run across that in there. So let's put it all together. Serial in-vehicle networks need a procedure control bus access. And I'm just giving you some examples again. There's so many, quite a few different systems in there. One of them is a master-slave system. Okay, there's also a multi-master bus system. In a master-slave system, one controller acts as a master to control the bus access and communication. It might have the gateway in there. Gateway seems to be an issue with cars. If you work on Chryslers and stuff, you got to go to AutoAuth and you got to get okay and pay to get into Chrysler units to get in deeper besides just getting codes. But I'm going to digress here. So the master grants access to the slave in a defined and predictable manner. For example, before a controller starts the transmission of a message, it will check to see, is the bus available? Idle state. Listening before transmitting. If more than one controller starts sending a message, there could be a collision. Procedure to solve the collision, we call it an arbitration. Very important. The 1939 bus topology implies that no controller is in charge like the previous example. There is no central network controller or hub. No single controller acts as a master, and that is a huge benefit. So if the data link gets cut in half, devices on either side of the break should still be able to communicate with each other, but not with the controllers on the other side of the break. This is important knowledge when you are troubleshooting potential J1939 data link problems. And you know what? You can go in there and you can look at some of that stuff on the CAN bus. You can back probe and look for messages and so on. Okay, and I did this. I believe it was in OBD part 1, part 2. I did go a little bit in depth on that one, why and how. But anyway, you have another, printout of the cavity here. Now on the J Pro, okay, I can see if the controllers are talking, sending messages. Let me see if I can get my on over here. It doesn't show it too good. Okay, but basically you see these dashed lines here. So all my controllers that are on the bus, okay, when they chatter, when they talk, and it can tell me how many messages, and it's quite a few. Okay, and of course, I can see it. And you see the same thing in there in the green, So I can actually see if they're talking. And now I'm going to have to put 2 and 2 together. Like, shouldn't this one be talking? Why isn't it talking? Okay. And I'll be very honest with you. It can be a little bit of a nuisance. When you go and get your codes and everything, I find that the communication stuff, there are so many codes referring or to the communications, and I'm not sure if I'm thinking correctly or not. A lot of times, if it's got a code for this or that, I stop not necessarily putting priority of what I'm looking on my screen when it comes to diagnostic codes. You know, some of them are definitely pending codes. You know, so I try to look when it comes to communications for something that is a very hard code, and then in my mind it has to really relate to communication. The other communications, I'm kind of thinking they haven't necessarily affected a vehicle per se to kick codes to be alarming, because if there were that many issues that I always see on the screen, I'll be honest with you, that vehicle wouldn't be running at all. It would be sitting still someplace. So we sometimes get a little overwhelmed with that stuff. So that's my 2 cents here, guys. You know. Final example is utilize time division multiplexing. Simply put, time division multiplexing is communication devices time sharing a common signal path, such a pair of copper wires, the data link. Each communication device takes turns using the common data link to transmit this information. This information is a form of digital encoded data. Digital, again, 2 states, high and low, on and off. Specific patterns of these high and lows have a specific meaning. Okay? Each data device on the data link interprets the pattern of these highs and lows and knows what they represent. Each controller takes turns using common data link wire transmit its digital data encoded information. Now, this stuff here that, you know, again, speed of transmitting is so fast that it might appear as though the devices are communicating on a common data link at the same time. Everything comes back to speed. You know, I want to switch screens here a little. I want to say something with that slide over here. If you are somebody that's going to put something on a vehicle, maybe you want to put on some devices that are going to keep on following drivers or whatever. You guys know there's telltale devices that get incorporated into our systems, and that's why you see multiple plugs coming out. Somebody's breaking in there, going in there, and so on and so on. Those guys, in order to make it happen, to make sure that information is accurate, they will get into the messages. They will get into data logging big time. Okay, there's instruments that they use that you can go in there, and you got the software. You can look at every single message, everything that happened and occurred, and they do that because also after the fact, if something goes wrong, they need to go backwards and see, what happened? Did we screw up? Why aren't we giving this customer enough information, the right information? So they have to work with those types of messages. Now, I have run across, to be very honest with you, now us guys as a tech, that sometimes can be annoying, you know, because I've had to disconnect their stuff to actually make sure I'm able to correctly diagnose what's in there. And to me, once in a while, that gets annoying, and that tells me somebody didn't marry this stuff together. And I do run across that quite often, more often that, you know, it's not just a very rare occurrence. So let's see what else we can get into. The high rates of speed over J1939 can be an issue. High frequency affects the amount of capacitance between 2 data links. You know, it's a phenomenon, okay? It's a phenomenon. That phenomenon distorts the shape of the digital waveform, and the CAN transceiver located in each controller might not be able to distinguish between the differences. You can call it logic 1, logic 0. Remember the zeros and ones and so on. So why the twisted wires? The data link conductors are twisted together to help provide immunity magnetic fields. By twisting wires together, any voltage induced into the wires by magnetic fields will be equal on both wires. And that's not the only reason. The twisted wires are coded yellow and green, you know, but again, don't take this as a given, okay? I see different colors in there too, you know, depending on, you know, is it 1708 or whatever. So don't necessarily hang your hat on green and yellow, okay? Also, SA standard for J1939 data bus requires a twist through a full cycle once per centimeter, okay? 2.5 times per inch. I like inches. At either end of the data bus is a terminating resistor to prevent twisted pair from acting like an antenna to attract signal interference and suppress data signals at the end of line to prevent data collision. And we'll get a little bit more into that, you know. The CAN transceivers are also designed to look at differences between CAN H and CAN low, CAN high and CAN low, not the voltage levels referenced to ground, okay? And we refer to that as a differential voltage. Here's an example, you know, you got a bad signal, you got a good signal, and we will get more and more into that, you know, and if you look at it, you can see, you know, the differences. You'll pick it out right away, you know, what's good, what's bad, okay? Changing magnetic field causes voltage noise to be induced into both conductors. The noise can be interpreted as logic high and change the meaning of the message. And this is why we so emphasize on this wiring. It is so, so important. Remember I mentioned garbage in, garbage out. You got to maintain the wire integrity. Even replacing with ordinary insulated wire could cause a communication issue between the modules. Okay? Simple explanation of the capacitance. Capacitor is a device. If you went through electrical courses, you know, you know what they are. You know, you've had them as condensers, or you had them years ago. You know, they suppress noise and so on, which opposes changes in voltage. However, capacitance in and of itself is the ability to oppose voltage changes or fluctuations. So I'm going to give you an example. Two adjacent conductors can function as a capacitor. This capacitance is usually small unless the conductors are close to each other for a long distance. This can be unwanted capacitance between isolated circuits. The stray capacitance can allow signals to leak between the circuits. Call it crosstalk. It can be an issue in circuits utilizing high frequency. Hopefully, this gives you another reason to maintain wire integrity. Impedance, here's another characteristic. So I'm going to try for a simple explanation towards the 120 ohm resistor that you might have heard about. But before we get into that, okay, if you guys remember before we had cable TVs and stuff, we had the TV antenna, you know, they were cables, TV antenna cables, are used for relating, excuse me, let me back up, okay? I'm going to use the old TV antenna cables that you might remember years ago before the cable, too many cables here, guys, for relating impedance to J1939 cable. Those old TV cables, they were often specified in ohms. You know, if you went out to the store, I think my little antenna was screwed up or something, you wanted to match what we call the impedance characteristics. So you had a couple of choices. 300 might be a 300 ohm, might be a 75 ohm, you know, impedance characteristic. And I'm saying that on purpose because you cannot measure this with an ohm meter, even though I said 300 or, you know, whatever the case may be. The J1939 cable, it's got the same characteristic impedance. However, it is 120 ohms. Okay, that portion with this characteristics can't be read with an ohm meter. Okay, it's not the same 120 ohm terminating resistance that you guys keep hearing about. Okay, but the whole idea is it's another reason to assure cable integrity. You know, another requirement for the J1939 cable is length. Backbone, okay, the whole shebang, front to the end, should be no longer than 40 meters. Stubs connecting controllers, you know, now I'm going to go to different controllers, should be no longer than 3 meters. Everything relating cables so far are meant to help maintain accurate data transmission. So if you have deficiencies in this cable, right there could be your issue, communication issue. So keep that in mind. Okay? Now, the terminating resistors. This is the real resistance that can be measured. Terminating resistors are used to minimize standing waves, quite often referred to as echoes or reflections. Note, think about speakers. You're out in a huge outdoor concert, okay? Speakers are spaced far apart. closest speaker gets mixed with a delay, and there is a delay, you know, and all of a sudden you're trying to hear that singer give a nice little song. It's like, what the hell was he or she singing? I can't understand the words. Well, the same thing can happen, you know, with our data links in controllers. They can't tell what is a reflection and what is the next message. You know, they're gonna be confused. The terminating resistors cause the signal energy to absorb, leaving no energy for these reflections. That's why you have them in there. The terminating resistors also provide a relative low resistance path for current to flow between CAN H, CAN high, and CAN L, CAN low. Remember the capacitance and voltage differential? This permits capacitance in the system to rapidly discharge. So now, if only one chain 1939 terminator resistor is missing, the vehicle will probably, and you got to hang your hat on probably. This is not always, I'm not saying it will. Probably, maybe, whatever you're comfortable, not show any symptoms. However, if both terminating resistors are missing, chances are pretty good there will be no communication for sure. Okay? So in summary, multiplex electrical system reduces wiring. Control modules transmit messages by controlling the voltage difference between two wires of a data bus. Control modules check the data bus for messages. Any module on the bus may transmit a message if data bus is free. Message protocol is programmed into all the modules on the data bus to instruct the modules on message priority. When a message is transmitted, the first portion of the message informs the other modules of the message priority. All the control modules connected to the data bus can, however, hear all the messages being transmitted. So if a message being transmitted on a bus isn't required, remember in the beginning, you know, you're talking to me, but I could care less. One ear in one ear, out the other. That module will disregard the message without any further processing. So right there, that last line goes back to my very first slide, second slide, whatever it was. I was talking about all of us, selective hearing. Okay? And this is an example of, you know, backbones and the stubs and so on and so on. Now, turn on this truck. And you're looking at the dashboard, and the dashboard says all systems are okay. Freaking really? How the hell do they know? Does that mean they're sending me a message that they don't need us anymore? They don't need me? I hope not. I just had to throw that in there. There will never be a day that they will not need us, guys, all day long. It ain't never gonna happen. Now, before I get into the questions real fast, I want to do something. Now, this is about an active brake assist, a little bit of an issue. Okay, I believe I got it from via NHTSA, but I'm going to read something real fast. DTNA, Daimler Truck North America, broadened its inquiry to also consider whether lighting later installed by truck equipment manufacturers, TEMs, or you might know them as final stage manufacturers during the multi-stage vehicle production process had an impact on the brake lamp display on these vehicles. They're having an issue here, okay? They're having an issue on some Freightliners and so on and so on. Western Star, okay? Brake light issues. Brake events. So they're in the middle. To conduct this assessment, DTNA sought to understand what ABA software, ABA again, active brake assist, packages are involved in final stage manufacturing of these vehicles, and how the wiring for the vehicle lighting is completed by that final stage guy. DTNA investigation found conflicting information about how TEMs may connect vehicle lighting, with certain TEMs using their own modules to control vehicle lighting functionality, and with others using a particular connector that might not receive the ABA, that's the active brake assist, brake input signal. Right? And it just goes on and on and on, okay? And this is new too. Given the variation of TEM processes, DTA continued to investigate this issue into August 2024 in order to better understand not only TEM production practices, but also the actual effect on the vehicle brake lights depending on the TEM's practice. All right? So I'm not going to go anymore, but again, it wound up doing a recall. So now I want to do something real fast before we wrap this up. Okay. So over here, I'm by myself right now. I'm going to turn the camera down a little bit. You know, it's just me. I'm talking. It's not dead air. So hopefully this will work a little bit better over here. You don't need me see my face. Okay? So here, okay, and I'll read it to you. Okay. I have a nice little, I can zoom in over here like this. Okay? And this is from Detroit, if you see over here. Let me put my thing down, okay? And there's an issue with the harness, okay? So after treatment harness. So I'm gonna read this real fast, okay? For GHG17, anybody remember what the GHG17 is? If you watch my OBD2 one, I brought that up on emissions, greenhouse gas, 17 engine. The main after treatment control module, ACM, shifted from a Daimler truck, North America, vehicle OEM, to a Detroit part. Two issues with this. Harness shows chafing on the branch to the 21 pin. Soot sensor, harness and ACM, okay, after treatment system. Control module, ACM. Show corrosion of the 21 pin connector. So for the sake of time, it goes on and on and on, what to look for and everything else. And this is what I actually wanted to. Let me zoom in over here. You're looking at the harness here. I got it here. It's the same as in that picture over there. And I'm going to zoom in, and hopefully I want to prove one point. So when we get complicated, we talk about all the multiplexing. We can talk about we can talk about speeds, and we can talk about anything that you want. We can talk about electrons, relays, and everything else. But when it's all said and done, guys, okay, you see here, see this pin? You can see it all screwed up here. And I will look on the other end. You see this over here? Without me zooming in, it lost connections. The whole issue with this communication boiled down to this, guys. We're right back to connections, integrity, and here we have that whole harness. It was easier to get the harness. I have taken harnesses apart. I have taken pins. I've refurbished it and all that stuff. But to be very honest with you, okay, sometimes it's much easier, and I'll get this camera up a little bit here again where it belongs. By the time you mess around with this stuff and you go and do everything, and before you know it, you know, it comes back again, it ain't working, comes back next week, comes back in a month. It's like, you know what, screw it. I did not create the problem. Throw a new harness in. At least from that point on, if anything becomes an issue, it's not that part. It's not the part that I fixed or tried to do. So again, let me find my little clicker here, and there's ample room for questions, okay? And a lot of the questions, they did come up during the chat box. I always love it. You guys do such a great job of answering the questions. You're helping me out. And like I said, I truly, truly appreciate that. The other thing I want you to do real fast is, if you want, please take a snap of that, okay, that barcode or whatever it is, and that's your way of going to Dorman and saying that, you know, hey, and to be honest with you, I have never gone on there. I don't even know what kind of survey it is or whatever, but I understand it's a good way of letting them know, you know, do you like what we do? Do you like what we don't do? Or I'm hoping there's a box or something in there that will also say, hey, how about, you know, giving us this kind of a course, you know, and blah, blah. In the future, let's do this and so on. So take a quick snap of that if you guys can. Okay? So I'm going to wind it down. Excuse me. I know it went quite a bit longer than usual, you know, but hopefully this all helped you out. And guys, stay safe. Thank you for what you're doing. You're the backbone of the industry. If it wasn't for you guys, we wouldn't have the safe roads out there. Okay? You're the guys that go underneath it. You're the guys that actually physically make sure those vehicles are safe. Okay? I can get any dummy out there to look at 10 tires on a vehicle and say they're brown and black. Okay? If the industry can't figure that out, there's something wrong. But, however, it's that side of the vehicle, that underneath, the inside, that they need us to make sure everything is working correctly. So thank you again, guys. I appreciate everything you do out there. Thank you.